Today we will discuss about local search algorithms. In the previous classes we have studied about blind search techniques. Blind search techniques. Search techniques. In these blind search techniques, the searching is based on blindly. That means there is no direction. Without direction, we will perform the searching process to achieve the optimum values. So, without direction, without proper direction or guidance, proper direction or you can say guidance, we will perform searching. Okay, searching in solution space. Okay, so that is what is happening. So examples of blind search techniques are, we have already studied full blind search and depthful search, DFS. We have seen algorithms also. Today we will discuss about local search algorithms. So what is local search? So how the searching is local search algorithms. So here we will see how the searching is differed from blind search techniques. So in local search algorithm, searching is mostly done in the local neighborhood of the given solution. So if you are given a solution, initial solution, so your next solution or you are searching for next solution, it will be in the immediate neighborhood of the given initial solution. So this is what is happening in the local search algorithm. So let us say I will draw a diagram so that you will understand. Say for example, if you are having a big solution space, something like this is the entire search space. So if the initial solution is here, so which is represented as dotted, so your next searching will be in the local neighborhood for this solution. Let us suppose this is x1. So your x2, that means the next solution will be in the local neighborhood. So you can see this one, that means this area we will call it as local neighborhood. Okay, this is the local neighborhood for x1. Local neighborhood for x1. X1 is the initial solution. So you will perform the searching within this region to find best optimum value. Okay, so that is why we will call it as a local search. So in this local search algorithm, we will study different techniques. So first we will study about hill climbing algorithm, and then next we will study about simulated annealing technique, and the third we will study about taboo search technique. Okay, so let us see one by one. We will go to next. First we will study about hill climbing algorithm. Okay, in this hill climbing algorithm, how the searching is done in the local neighborhood. Okay, let us see. So by this time you should understood that optimization is the process of finding or searching the best value, okay, best value of x in such a way that your objective function is maximum or minimum. Okay, so we will study on next algorithm. Next we will study the first technique. You can put the heading hill climbing algorithm. So what is hill climbing algorithm? Hill climbing algorithm is a simple local optimization technique which climbs up the hill until a local optimum is found. So that means it is a simple local optimization method which climbs, that means your searching will be in the form of climbing up the hill. That is why the name is given as hill climbing algorithm, climbing up the hill until a local optimum or global optimum is reached. Actually, the main disadvantage for this algorithm is local optimum, okay, optimum is found. Okay, so here the searching will be in the form of moving up the hill. Okay, it will be in the form of moving up the hill until you reach the local optimum. Okay, so this algorithm, it works by iteratively searching the new solutions within the neighborhood of the current solutions. So let me explain with the diagram. Let us suppose this is the x variable and this is your objective function f of x. This is your objective function obj function, objective function, we will call it as objective function. So if you are having a function, the shape of the objective function is something like this. Okay, this is your objective function f of x. Now what you have to do is you have to move up. Okay, you can see this algorithm. Let us suppose you started at this is the initial location x1. So you have to climb. You can see the objective function looks like a hill and you have to move upwards. Here this is your global optimum. So you have to move from x1 point to up to x star optimum. So you cannot move directly. You have to move step by step. That means you have to generate so many intermediate solutions like x2, x3 and x4 and so on until you reach the x star. You can see at x star your objective function is maximum. Okay, so you have to climb up the hill until you reach the global optimum. Okay, that means your algorithm will iterate step by step manner. That means during each iteration it will produce one local solution. At first iteration it will produce x1, at second iteration it will produce x2 and x3 and so on. You have to stop the algorithm until you reach the global optimum. You can see at this global optimum the solution x is denoted as x star, and the corresponding value, that means f of x star, it will be maximum, it will be very maximum. So this is our objective. Okay, so this is we'll move step by step manner only. That means we will search the solutions. That means your intermediate solutions, it will dependent upon the initial solution. Okay, and also it is a local neighborhood. So as a result, there may be some problems. The main limitations for this global hill climbing algorithm are: three problems can occur. First one is local maxima. You can see from this. The curve is something like this. You can see, say for example, if you started the searching process, if you move from here, let us suppose this is the starting position, you may reach here and you may climb this as optimum solution. Actually this is not optimum solution, it may be maximum, but when compared with global search space, this is local maxima only. So your hill climbing algorithm, it suffers from limitations like local, first one is local maxima or minima. So local maxima means at this point you may think that you have reached the maximum value. So when you compare with this x star with local values, it will appear that you have achieved the maximum value, but in general when you compare with this location, it is still lesser value only. So sometimes your algorithm, your hill climbing algorithm may stuck at this position. So this is called x local maxima or minima. Okay, so in this case it is a local maxima. Okay, sometimes if your algorithm, if you start from here, if your searching process has started at x1 dash, so you will move in this direction. Okay, you will move in this direction. So when you reach here, if the objective function curve is very flat, means you may think that you have reached the maximum value. So that is the main problem. Sometimes you may have flat surface. Okay, so which one you call surface? So which we will call it as a plateau. Okay, plateau. So plateau is one type of surface where you will have uniform values. Okay, uniform surface. That means you can see the neighborhood of this point will have equal f of x values. Okay, so you cannot go in this direction or in this direction. Okay, so you need to understand that ultimately optimization is the searching through the space. Okay, so another problem is the ridge. So you can see ridge, you can assume a thin line. If you see the mountains from top view, all the peak mountains will have a line of edges. Okay, peak of edges. So if you take any point on that edges, it will have the peak value. So if you move in either of directions, it will have minimum value. Your f of x will be minimum value. So sometimes your algorithm may be trapped in the ridge type surface. If your f of x is having ridge type surface, so your algorithm will not move in any direction. Okay, it will be stuck at that position. Okay, so 3 limitations are there. You please go through that. So let us see the standard algorithm. Okay, what is the pseudocode for this? Let us write hill climbing algorithm. So by this time you could have understood that. So in each iteration, in first iteration you will generate first intermediate solution, which we call it as the initial solution. With the help of initial solution you will generate x2. Okay, x2, that means you will add some step delta to this. So for generating x3 you will add the step size, so and so on. Ultimately you have to add that value until you reach the x star. X star is the previous value x of n minus 1 plus delta. Okay, so how do you get x3? x2 plus delta. So that you need to remember. So again I will write x1 is the initial solution. It can be randomly assigned. And x2, how you will generate? x1 plus some delta. This is your step change. How you will generate x3? x2 plus delta. So you have to generate until you reach x star, x of n plus delta. Okay, this is how the hill climbing algorithm will work. So this is how for each iteration you have to generate candidate solutions. So let us write the algorithm for this hill climbing. This is a pure hill climbing algorithm. So just I am using different colors. So first you have to specify the inputs for this algorithm. So this hill climbing algorithm, you have to give the initial solution, which we call as a S, and then you have to give the objective function f and some control parameter c. Okay, and control parameter c. Okay, this control parameter c, generally if you see, it consists of the maximum number of iterations, okay, that you can specify here. Generally this is that is a thing. We will specify the control list parameters here, and then the inputs. These are the S is the initial solution. You can take it randomly, and F is the objective function, and C is the control parameter. Generally, control parameter means you have to specify the maximum number of iterations. So these are the inputs you have to specify, and then loop variable, because the algorithm will run infinitely. So next step is you have to specify the termination condition. That means you have to run the steps. Okay, run the steps in infinite manner. So while the termination criteria is not reached, that means you can write while not termination criteria, which is a function of, generally you can write SFCI, or you can specify the C, just control list parameter. While termination criteria is not reached, you keep on generating the candidate solutions. So let the candidate solutions be S dash. S dash is generated with the help of change function. So for this change function, you will give the initial solution and then the control parameter. So here the control parameter may include you can say distribution function, some random distribution function, okay. So this is also comes under your control parameters, okay. C, okay. So if you give the inputs S and C, the change function will compute the new solution S dash, okay, new solution S dash. So after getting the new solution, what you have to do means, that means this S dash, you can see this S dash, you can have a set of candidate solutions, okay, set of candidate solutions you will get, because you may have so many number of neighborhoods, okay. For a particular initial solution, you may have n number of neighborhood solutions, okay. So out of this S dash, you have to choose the best one, okay. You have to choose the best one. So you will apply the best function, which takes the input S dash and F. So with respect to S dash and F, you choose the best one, and then in the sixth step, so out of these candidate solutions, okay, and again select the best solution and store it in S. So here you can see B set of best solutions, and then you can keep on you can implement the loop variable I is equal to I plus 1, and the eighth step you can put ny, and ninth step you will get the output. So output will be in the form of D, okay. So you will get the best solution is optimum solution. So here the logic is simple thing, you apply the change function to get the new solution S dash, okay, and out of this you have to select the best one, whether S is best or S dash is best based on the objective function F, and then this will be replaced with S, okay, because again you have to run the loop. So this loop will be run up to n number of iterations or up to maximum iterations, okay. So you can see this loop will run continuously, it goes on continuously. So this will here the stopping criteria is, so you have to specify this one, okay. You have to specify the maximum number of iterations. Say for example, you can set the max iteration as 10,000. That means after 10,000 loops, so you will get the best solution. So this change function, it will take input S and C based on these two parameters, new solution S dash is a new solution, and best solution what it will do means it will compare which one is best, okay. So whether S is best or S dash is best based on F, okay, that is stored in B. So once B is stored, you try to replace within the S again, okay. Again you check the termination criteria. If the termination criteria is not reached means again you run the loop, okay. So here the termination criteria is this one. Here you can see in the change function, you can see the change function, it is dependent on the distribution, okay. So you can take some uniform distribution or something like random distribution function or exponential distribution function like this. So this is a generalized hill climbing algorithm. Okay. So what I want to do means I want to show you a little example so that you will understand in a more. So let us take, for simple illustration, the example we will take. Example, f of x is equal to x1 plus x2 plus x3. So let us suppose the initial solution is something like this. Let the initial solution is 0 0 0. So first we will compute the x1, that is the first iteration. It is given by x of 0 plus delta. Let us suppose the delta is some random value taken from normal function which is having 0 and 1. Let us suppose we will get 0 0 0 plus the delta. What is the delta? You can take some sampling random function based on some normal distribution. Let us so 0.2 we got, 0.1 you got, 0.5. Let us add it. What is x1? We will get 0.2, 0.1, 0.5. So now you will calculate which one is better. Let us suppose this is a maximization problem. So you substitute in f of x. You substitute x of 1 in f of x, and you substitute x of 0 in f of x, and you compare these two values. Clearly f of x1 is greater than f of x of 0. So therefore, which is the better solution? So for first iteration, this is the first iteration. Which is the better solution? Better solution. So clearly x of 1 is the better solution. So this is the actual solution. So x of 1 is the better solution. Is the better solution. Since f of x1 is greater than f of x0, this is the better solution. Okay. Now take the second iteration. During the second iteration, how do you compute x of 2? Better solution. This is the B is the better solution. Better solution plus delta. I already told you delta is a sampled value from distribution function 0, 1. So which one is a better solution? X of 1 is a better solution. So what is x of 1 here? 0.2, 0.1, 0.5. 0.2, 0.1, 0.5. And delta, what is the delta value? It is a random value only. You can take 0.6, 0.4, 0.5, something like that. You compute x of 2. So 0.8, 0.5, 1.0. So again you compare, you perform the comparison. F of x of 2 and f of x of 1. So clearly it is greater than. So your best solution is x of 2. So again you take the third iteration. In the third iteration, how do you calculate x of 3? The best solution plus delta. So again you perform comparison, all these things. So up to the maximum number of iterations you have to perform this algorithm to reach local optimum, local or global optimum. Okay. So this is how the algorithm works. Thank you, students.